Welcome to The Explainer. Today, we're gonna unlock the invisible forces that literally shape our modern world. We are embarking on a journey to explore the incredible relationship between moving charges and magnetism. It's this fascinating area of physics that's absolutely gonna change how you view the devices surrounding you right now. So think about this for a second. What actually happens when electricity and magnetism are forced to share the exact same space? For centuries, humanity thought of these as completely separate things, no connection whatsoever. But as we'll see today, their interaction is the hidden engine driving almost all of our modern technology. Okay, let's dive into this roadmap. We've got 5 main stops today. First, the 1820 discovery, followed by the Lorentz force, motion in magnetic fields, the Biot-Savart law, and finally, Ampere's law and solenoids. It's a beautifully structured progression from a happy historical accident all the way to applied physics. All right, Section 1, the 1820 discovery, an accidental connection. We often think of major physics breakthroughs as the results of, decades of complex, abstract math. But the intimate connection between electricity and magnetism, it actually came down to a surprising, very human moment of accidental discovery. Just take a look at the historical momentum here. In 1820, a simple connection is noticed. Fast forward just a bit to 1864, and James Clerk Maxwell unifies the laws. By the late 19th century, we've got the discovery of radio waves. That single spark in 1820 directly triggered the immense technological boom of the 20th century. It is just amazing how rapidly our understanding of electromagnetism accelerated human progress. Let me set the scene for you. It's the summer of 1820. Danish physicist Hans Christian Ørsted is giving a standard, run-of-the-mill lecture demonstration. He has a straight wire carrying an electric current, but he notices something weird. A nearby magnetic compass needle suddenly deflects, and it doesn't just point at the wire, it aligns tangentially to an imaginary circle perfectly perpendicular to the wire. So, the crucial point here is this. Ørsted heavily investigated this deflection and arrived at a really profound conclusion. Moving charges, or currents, produced a magnetic field in the surrounding space. It wasn't the wire itself, but the literal physical movement of the electrical charge that created the magnetism. This was the foundational rule that forever linked electricity and magnetism. Moving right along to Section 2, the Lorentz force, from source to effect. Now that we know how these fields are created, let's shift our focus. Because it's one thing to know how a field is made, but how do these invisible fields actually impact the physical world around us? Let's break down the Lorentz force formula, originally formulated by H.A. Lorentz. The Lorentz force is simply the combined force acting on a point charge due to both electric and magnetic fields. Think of it as just the sum of 2 pushes. Actually, scratch that. It's the combination of 2 specific forces. The electric force, represented by the E, and the magnetic force, represented by the velocity vector crossed with the magnetic field vector, B. Now, let's compare these 2 forces side by side, because there is a massive distinction here. The electric force acts on a charge whether it is stationary or moving. Doesn't matter. But the magnetic force, it strictly requires a velocity, that V you saw in the formula. If a charge isn't moving, the magnetic force is absolutely 0. Only a moving charge feels the magnetic push. And because the magnetic force involves a vector product, it operates in 3 dimensions. Okay, I highly recommend literally holding up your right hand right now to visualize this. Imagine grasping a wire with your right hand. Point your extended thumb in the direction of the current. Notice how your fingers naturally curl around. That curl represents the exact circular direction of the magnetic field. It's such a fantastic, simple way to grasp the complex physics happening right in your own room. Okay, Section 3, motion in magnetic fields, trajectories. We have the forces, sure, but how do they actually make things move? Well, the Lorentz force dictates the exact paths of charged particles, and as you'll see, the resulting visual paths are mathematically beautiful. And this brilliantly illustrates that idea. When a charged particle moves purely perpendicular to a uniform magnetic field, the magnetic force acts as a centripetal force. It constantly pulls the particle inward, perfectly trapping it in a continuous, endless circular orbit. No way out, just a perfect circle. But what happens if the particle's velocity isn't perfectly perpendicular? What if it's moving slightly parallel to the magnetic field lines too? Well, that parallel component of velocity remains totally unchanged by the magnetic field. This essentially pulls that circular motion forward into a continuous spiraling helix. It's exactly like stretching a spring out through space. Section 4. Calculating fields. the Biot-Savart law. Up until now, we've looked at single particles and individual concepts. Let's zoom out a bit to the macroscopic world. If we have a wire of literally any arbitrary shape, how do we mathematically predict the invisible magnetic forces it generates? For that, we turn to the Biot-Savart law. The Biot-Savart law is a mathematical equation that defines the magnetic field generated by an infinitely small element of steady electrical current. Basically, it allows us to take a microscopic, tiny slice of current and calculate exactly how much magnetic field it contributes to a specific point a certain distance away. And there are a few key features to keep in mind here. First, it obeys the superposition principle, meaning you can just add up the fields of all the tiny wire segments to get the total field. Simple enough. It also follows an inverse square law, meaning the magnetic field drops off significantly the further you get from the wire. Finally, the direction is strictly perpendicular, and the strength is highly dependent on the exact angle between the wire element and the point you are measuring. All right, our final stop, Section 5, Ampere's Law and Solenoids. We're going to take all these foundational laws and apply them to a highly symmetric, real-world application that makes so much of our modern electronics possible. But first, we need to introduce Ampere's circuital law. This is an alternative and, frankly, a much simpler way to express the relationship found in the Biot-Savart law. It relates the magnetic field on an open surface's boundary directly to the current enclosed within it. If you're familiar with electrostatics, it acts as the exact magnetic equivalent to Gauss's law. Now, what's really interesting about this slide is how we apply Ampere's law to a solenoid. A solenoid is essentially just a long wire tightly wound into a helix. Look at the magnetic field lines for this finite solenoid. Do you see how between the neighboring turns, the circular loops of the magnetic field actually cancel each other out? This cancellation forces the magnetic fields to combine and straighten out right down the center. And when we stretch that out into an idealized, very long solenoid, the results are incredible. The magnetic field outside drops to near zero, but inside this long cylinder, the field becomes perfectly uniform, strong, and parallel to the axis. This uniform controlled magnetic field is absolutely crucial for driving modern technology. Okay, let's pull the whole shebang together. Because wires carry moving charges, they create magnetic fields. And as we learned with the Lorentz force, magnetic fields exert forces on moving charges. So logically, two current-carrying wires placed near each other will physically interact. If parallel wires have current moving in the exact same direction, they'll mechanically attract each other. If the currents are opposite, they repel. And get this exact principle of magnetic forces acting on current loops is the working principle behind the moving coil galvanometer, which is an essential instrument used to detect and measure electrical current. It's a perfect physical demonstration of everything we've covered today. I want to conclude this explainer with a really provocative paradox directly from our source text. We established that moving charges create magnetic fields, right? And only moving charges feel magnetic forces. But what if you move alongside that charge at the exact same speed? Think about it. From your perspective, the relative velocity is zero. That means the magnetic force completely vanishes. This brilliant thought experiment proves that electricity and magnetism aren't just isolated forces. They are fundamentally linked to our frame of reference in the universe. A wild and profound concept to leave you with until our next explainer.